Imagine standing outside on a clear night. The air feels still, and the sky seems silent. The stars appear frozen in place, like grains of salt scattered across a black table. Nothing appears to move. Nothing reveals its true distance or age. The night sky gives the illusion of simplicity. It looks flat. It looks calm. It looks empty. But that is only because our senses are not designed to perceive the scale of the universe. What seems like emptiness is structure. What feels like simplicity is complexity. And what appears motionless is in truth a cosmic ocean in which everything is drifting. Cosmology is the attempt to understand all of it. Not just the stars we can see, but the space between them. Not just the planets around our sun, but the galaxies beyond our imagination. Astronomy observes objects. Cosmology asks why those objects exist. Astronomy points telescopes at stars. Cosmology asks how space itself behaves. Astronomy catalogues worlds. Cosmology tells us how worlds became possible. Cosmology is not a branch of philosophy. It is not speculation or myth. It is a science built from a sequence of unavoidable observations. A scientist does not get to choose the kind of universe they prefer. The universe reveals what it is, whether we like it or not. Cosmology exists because there is data that demands an explanation. Evidence forced us to accept that the universe has a history, that it changes, that it evolves. The night sky is not a museum of eternal objects. It is a time machine. Every photon that reaches your eye has traveled across space for an unimaginable length of time. Light from the moon takes a little more than 1 second to arrive. Light from the sun takes a little more than 8 minutes. Light from the nearest major galaxy, the Andromeda Galaxy, takes more than 2 million years. That means when you look at the Andromeda Galaxy, you are seeing that galaxy not as it is today, but as it was before humans existed. Your eyes are receiving ancient information, delayed by the finite speed of light. The universe behaves like a vast archive of the past. When we build telescopes that see farther, we are not just increasing distance. We are increasing history. We are observing younger versions of galaxies, and even younger versions of the universe itself. At the farthest distances, we detect a universe that is not recognizable. Galaxies are smaller. They collide more often. There are no planets yet. There are no stars for a time. Go farther still, and there is only an opaque fog of primordial plasma. Push even deeper, and there is a moment when atoms did not yet exist. The deeper we look, the younger the universe becomes. Cosmology does not ask you to imagine these things. Cosmology shows them to you. Many great ideas in science began as speculation. Cosmology began as the opposite. The data arrived first. The explanations came later. At the beginning of the 20th century, scientists assumed that the universe was static, eternal, unchanging. The dominant belief was that space existed forever and would continue forever in an unaltered form. That belief felt safe. It was intuitive. It matched the calm stillness of the night sky. Then telescopes improved, observations deepened, and everything changed. We discovered that the universe refuses to sit still. The discovery that space is expanding did not begin with a theory. It began with light. When the light of a distant galaxy stretches toward longer wavelengths, it shifts toward the red end of the spectrum. This shift is measurable and repeatable. It is not metaphor or poetry. It is data. When scientists measured the redshift of galaxies farther and farther away, they saw a pattern that could not be ignored. Almost every galaxy is moving away from us, and the farther the galaxy is, the faster it recedes. Space itself is expanding, carrying galaxies with it like leaves, floating apart on a rising tide. This was the first sign that the universe has a past. If everything is moving away from everything else today, then yesterday they were closer. Go back farther, and space shrinks. Continue far enough back, and the universe becomes smaller, hotter, and denser. This leads to a profound and unavoidable conclusion. The universe had a beginning. Cosmology emerged from that moment, not from the concept of a beginning, but from the need to understand the evidence that revealed it. This is what separates cosmology from mythology. A myth begins with a story and looks for meaning. Cosmology begins with measurement and looks for truth. The telescopes that revealed expansion were not built to support any theory. They were built because humans are curious, and curiosity changes the world. The second great observational pillar came from a completely different direction. Scientists predicted that if the universe began in a hot and dense state, there should be leftover heat still cooling today. They expected that faint relic radiation should fill all of space. It should not come from any specific galaxy or star. It should come from every direction equally. In 1965, two radio engineers were calibrating an antenna and found an annoying signal they could not eliminate. It was uniform. It was persistent. They thought it was a hardware problem. They thought it was pigeon droppings inside the instrument. They cleaned the equipment. They rebuilt the receiver. The signal did not disappear. They had accidentally discovered the afterglow of the birth of the universe. This faint radiation is called the cosmic microwave background. It is the oldest light the universe allows us to see. It is a message frozen from a time when the universe was only a few 100,000 years old. Its temperature is 2.725 Kelvin, just a few degrees above absolute zero. It is almost perfectly smooth, but not entirely. There are tiny variations, differences smaller than 1 part in 100,000. Those tiny variations are the seeds of everything that would later form stars, galaxies, and eventually planets. From that single observation, cosmology gained the ability to study the early universe directly. The cosmic microwave background is not a theory, it is a photograph. The moment the cosmic microwave background was detected, any idea of a static eternal universe collapsed. The data had spoken. Cosmology became a science of history. When we combine the observed expansion of space with the measured relic radiation, we gain a timeline. The universe was once hot. It cooled. Matter formed. Structures appeared. The universe did not simply exist. It unfolded. But cosmology goes even farther. It does not only tell us that the universe changed, it tells us how the change happened. The patterns in the cosmic microwave background reveal the shape of space itself. They tell us how much matter exists. They tell us the geometry of the universe. They even reveal that most of the mass that shapes the cosmos is invisible. Dark matter leaves fingerprints in the structure of galaxies. Dark energy alters the expansion of space. Every piece of modern cosmology begins with evidence. Every conclusion must explain that evidence. Cosmology is a map, not a map of places, but a map of evolution. We are not simply learning where everything is, we are learning how everything came to be. The purpose of cosmology is not to make us feel small, it is to reveal that the universe is knowable. You and I inhabit a universe that is not a random explosion. It is governed by laws that hold everywhere. The same physics that moves a falling apple also shapes galaxies. Cosmology tells us that the universe is understandable, and because it is understandable, we can trace how galaxies formed, how elements emerged, and how stars created the ingredients for life. Cosmology shows that we are not separate from the universe. We are part of its story. The night sky is not quiet, it is speaking. Cosmology is learning to listen. The night sky tempts us to believe that we are the center of everything. When we look up, it feels natural to imagine ourselves at the origin of the cosmos. The stars surround us in every direction, and our senses quietly suggest that the universe revolves around our point of view. But cosmology is the practice of correcting our senses. It reveals that what appears obvious is often an illusion created by our limited perspective. When scientists discovered that galaxies are moving away from us in every direction, it would have been easy to assume that we must be located at the center. Instead, cosmology asked a deeper question. What is the simplest explanation that matches the evidence? If every raisin in a rising loaf of bread drifts away from every other raisin, then from the perspective of any single raisin, space appears to expand outward. The bread has no center on any individual raisin. Space behaves the same way. No matter where you stand in the cosmos, you see the same expansion. The universe is not expanding into anything. Space itself is increasing. The distance between galaxies grows even if the galaxies remain motionless within their local regions. This truth is difficult to feel because expansion is not noticeable on small scales. Space does not stretch the room you are sitting in. It does not stretch atoms. It does not stretch the distance between you and your chair, because gravity and electromagnetism hold those systems together more tightly than cosmic expansion can overcome. Only on the scale of millions of light years does expansion reveal its influence. Space is not a stage on which events occur. It is part of the event itself. When Edwin Hubble studied distant galaxies in the early 1900s, he found that their light was stretched. Not a little, but consistently. The farther the galaxy, the greater the stretching. Light that should have appeared blue appeared redder. Light that should have appeared red shifted deeper into the infrared. This stretching is called redshift. It is not a metaphor. It is a measurement. Light behaves like a wave, and when space expands, the wave itself becomes longer. Imagine drawing a wave on a rubber band and then pulling the band. The wave becomes stretched as the band stretches. The light from a distant galaxy behaves in exactly the same way. This discovery forced cosmology into existence. Scientists could not claim a static universe while observing light that indicated universal expansion. The data did not ask for permission. It demanded an explanation. Once expansion became undeniable, a second unavoidable realization emerged. If the universe is expanding today, then in the past, everything was closer together. Go far enough back, and every galaxy, every atom, every particle of matter and light must have been compressed into an unimaginably dense state. The universe had a beginning. Not a moment of creation in the mythological sense, but a physical and measurable origin point in time. For many years, this idea was controversial. It sounded too close to the concept of creation. Scientists resisted it for emotional reasons, not scientific ones. But the universe does not care about comfort. It cares about consistency. When multiple independent lines of evidence point to the same conclusion, it becomes difficult to deny. Expansion was not alone. Another consequence emerged. If the universe began hot and dense, then the early cosmos should have glowed with intense light. As space expanded and cooled, that light would stretch into longer wavelengths. Eventually, it would become microwave radiation. If the beginning happened, the relic light should still be everywhere. Scientists predicted that we should be able to detect this ancient afterglow. They even estimated its temperature. It should be a few degrees above absolute zero. Not 0 Kelvin, not 10 Kelvin, somewhere around 2 or 3 Kelvin. The prediction was precise. If the universe began in a hot, dense state, this radiation must exist. Then, something extraordinary happened. The radiation was discovered by accident. 2 engineers were testing an antenna designed for satellite communication. They kept hearing a faint noise that would not disappear, no matter how carefully they cleaned the instrument. They even removed nesting pigeons and cleaned away droppings that might have caused interference. None of it mattered. The signal was still there. It was smooth. It was uniform. It was everywhere. They had discovered the oldest light in the universe, the cosmic microwave background. The cosmic microwave background is a fossil of the early universe. Not a photograph taken later, but the earliest moment light could travel freely. Before that moment, the universe was too hot and dense for atoms to form. Electrons and protons could not combine. Photons were constantly scattered in every direction, trapped in a fog of charged matter. About 380,000 years after the beginning, the universe cooled enough for atoms to form. Electrons joined with nuclei. The fog cleared. Light escaped. that light is still traveling. When you place a radio antenna into the sky and remove all local interference, you are hearing the universe as it was in its first childhood. The temperature of the cosmic microwave background today is precisely 2.725 Kelvin. It is not 2 Kelvin, it is not 3 Kelvin, it is 2.725. Cosmology requires precision because precision reveals truth. When satellites later mapped this radiation across the entire sky, something astonishing was revealed. The light was almost perfectly uniform, but not entirely. There were tiny variations in temperature, smaller than 1 part in 100,000. These microscopic variations represent slight differences in density in the early universe. Regions that were a little more dense attracted more matter. Over billions of years, those slight differences grew into stars, galaxies, and galaxy clusters. Everything we see today was seeded by those minute fluctuations in the early cosmos. Cosmology does not show us a chaotic explosion. It shows us a universe with structure and patience. A universe that began simple and became complex through time. A universe where small imperfections in the early distribution of matter eventually led to the intricate cosmic web of galaxies we observe today. The more we studied these patterns, the more the universe revealed. The patterns confirmed something even stranger. The geometry of space is nearly perfectly flat, not curved in on itself like a sphere, not open like a saddle, but flat. Flat means that the rules of geometry we learn in school apply across the cosmos. Parallel lines remain parallel. Triangles add up the way we expect. The universe seems to balance on a razor edge between collapse and perpetual stretching. We do not yet know why the universe is so precisely balanced, but we know that it is. Cosmology transforms awe into understanding. It takes the night sky from a spectacle to a story. Every faint point of light is a reminder of how far we have come from assuming the universe was static and eternal. We now know the universe has a past, a present, and a future. It grows, it evolves, it allows complexity to emerge, it allows observers to exist. Cosmology is not just the study of everything, it is the study of how everything became possible. In the beginning of our story, humans looked at the sky and imagined that everything revolved around them. It was not arrogance, it was simply the most natural conclusion based on what the eyes could see. The stars circled overhead. The sun rose and set. The moon waxed and waned. We were the audience, and the universe seemed to perform for us. Only much later did we learn that the illusion of a universe centered on Earth was created by our limited point of view. Cosmology teaches us that the universe is not obligated to appear the way it truly is. It only shows us what we are ready to measure. We ask the sky one question: why does the universe look the way it does? The answer has taken centuries to assemble. Piece by piece, evidence forced us away from comforting assumptions and toward reality. The expansion of space showed that the universe has a history. The cosmic microwave background revealed that the universe was once hot and dense. The tiny temperature variations in that ancient light showed how structure emerged from almost nothing. These are not theories invented to explain the sky. They are consequences of what the sky demanded that we accept. When scientists studied the cosmic microwave background in detail, they noticed something remarkable. The small temperature variations were arranged in a pattern. Not random static, not noise, but a carefully shaped fingerprint of sound waves that once echoed through the infant universe. In the earliest moments, the universe was a glowing sea of plasma. Atoms could not yet form. Light scattered constantly. Pressure waves traveled through that plasma like ripples across the surface of a pond. When the universe expanded and cooled enough for atoms to form, those sound waves froze into place. The cosmic microwave background captured them. We are staring at frozen echoes of the first music of the cosmos. These patterns allow us to measure the amount of matter in the universe. They allow us to measure the amount of invisible matter. They even allow us to determine the overall geometry of space. The conclusion is astonishing. The universe is flat to within one part, in many tens of thousands. That is not a poetic guess. It is a measured property of space-time. A flat universe means that if you draw a massive triangle with beams of light that stretch across millions of light years, the angles will add up to exactly what you learned in elementary geometry. A flat universe means that the amount of matter and energy is balanced with exquisite precision. To understand how strange that precision is, imagine placing a pencil upright on its point on a smooth glass table. The pencil remains balanced for only a moment before falling in one direction. In the early universe, a tiny difference in the energy balance would have caused space to either collapse on itself or expand too quickly for structure to form. But the universe balanced perfectly. This delicate harmony is not fully understood. Cosmology does not hide the mystery. Cosmology collects evidence that will one day explain it. Another revelation came from studying how galaxies move. When scientists measured the rotation of galaxies, they expected the outer stars to move more slowly than the inner stars. The same way the outer planets in our solar system travel more slowly around the sun than the inner planets. But the measurements did not match. The outer stars were moving far faster than visible matter alone could account for. If only the matter we can see existed, those galaxies should have spun apart. Instead, something unseen provides the missing gravitational glue. We call it dark matter. It does not emit light. It does not interact with electromagnetic radiation. But it has mass. It has gravity. It shapes the universe. We confirmed dark matter again when we mapped the large-scale structure of galaxies. Instead of being arranged randomly, galaxies form long filaments and giant voids. Computer simulations that include dark matter produce structures identical to the real cosmos. Simulations without dark matter fail completely. Dark matter is not a guess. It is measured through gravitational lensing, where light bends as it passes near massive invisible structures. The sky becomes a lens, and the invisible becomes seen by its influence. Even more astonishing was the discovery that the expansion of the universe is not slowing down, it is speeding up. Scientists measured the brightness of certain exploding stars called Type 1 as supernovae, which act as standard candles useful for determining distance. When researchers plotted how fast galaxies were moving away, the result contradicted expectations. The universe is not merely expanding, it is accelerating. Something unknown is pushing space apart. We call this something dark energy. It is not a poetic term. It represents our ignorance. We know its effect. We do not yet know its nature. Dark matter pulls. Dark energy pushes. Together they shape the past and dictate the future. Cosmology teaches patience. It accepts the unknown without surrendering to mystery. Every time we pointed a more precise instrument at the sky, confusion gave way to clarity. The universe tells its story willingly, but only to those who learn its language. Light is its language. Motion is its grammar. Time is its narrative. The night sky we see with our eyes is not merely a scattering of stars. It is the visible surface of a deeper structure. Behind the stars are galaxies. Behind the galaxies is the cosmic microwave background. Behind the cosmic microwave, background is a realm we cannot see, a time when light could not travel freely and matter had not yet formed. And behind that moment, hidden from direct observation, may lie the greatest mystery of all: what set everything in motion. We do not claim to know every answer. We only claim to follow evidence wherever it leads. What makes cosmology powerful is not certainty. What makes it powerful is that it refuses certainty until evidence arrives. The universe is not shaped by imagination. It is shaped by fact. Yet the facts are more wondrous than anything imagination has ever produced. When we look into the depths of space, we are looking into the depths of time. The further we see, the younger the universe becomes. Eventually, we reach the horizon where light began. Beyond that horizon lies the birthplace of everything. We cannot see beyond it, but we feel the consequences of whatever happened there in every measurement we make. Cosmology is a discipline built on humility. The universe is vast. We are small. Yet somehow, impossibly, the universe allows us to understand it. The most astonishing truth is this: the atoms that form your body were forged in the heart of stars. The stars were assembled by the gravity of dark matter. The expansion of space allowed those stars to form at all. You are not separate from the universe. You are one of its outcomes, a product of its laws, a witness to its story. You are the universe, learning to look back at itself. In the early 20th century, almost every scientist believed the universe was eternal. The common view was that space existed forever in a calm and unchanging form. Stars might age and galaxies might move, but the universe as a whole was thought to be permanent and still. This assumption felt safe because the sky itself appeared still. When we look up, we do not see distant galaxies racing away. We see a quiet dome of lights that seem fixed in place. Our senses suggest stability, but nature does not care about what looks stable. It cares about what is true. The story of expansion begins with starlight. Light travels across the universe carrying information about distance and motion. The color of that light acts like a code. When something moves toward us, the wavelength of its light becomes shorter, shifting toward the blue part of the spectrum. When something moves away from us, the wavelength of its light stretches, shifting toward the red part of the spectrum. This stretching is called redshift. It is not a guess. It is a measurable consequence of motion. A young astronomer named Edwin Hubble began collecting precise measurements of distant galaxies. The method was simple in idea and astonishing in execution. First, identify a galaxy by its shape and brightness. Then use a special type of star inside that galaxy, a star whose brightness follows a predictable pattern. These stars act like distance markers. By measuring their brightness, one can determine how far away the galaxy is. After distance is known, the next step is to measure the shift in the light coming from that galaxy. If the light is stretched toward red, the galaxy is moving away. The data came slowly at first. A few galaxies showed redshift, then a few more. Eventually, the pattern became undeniable. Nearly every galaxy Hubble observed was moving away from us. Not just some galaxies. Not just galaxies in one region of space. Almost every galaxy in every direction. That alone was astonishing. But the universe was not finished with its revelations. The farther away a galaxy was, the faster it appeared to move. There was a relationship. Distance increased. Speed increased. The light became more redshifted. The pattern was so clear that Hubble could express it as a simple proportional rule. The greater the distance, the greater the recession speed. At first, people resisted the conclusion. If everything is moving away from us, does that mean we are at the center of the universe? The answer is no. The expansion does not place us at the center. Instead, every point in space sees the same pattern. To understand this, imagine a loaf of rising bread dotted with raisins. As the bread expands, every raisin sees every other raisin moving away. The bread does not expand from a single raisin outward. The entire loaf increases in size. Each raisin experiences the same pattern. Space behaves in that same way. The expansion is everywhere. No place is special. This discovery shattered the idea of an eternal universe. If galaxies are moving apart today, they must have been closer together in the past. As time rewinds, the universe becomes smaller. Keep rewinding, and the universe becomes extremely dense. The inevitable conclusion arrived. The universe had a beginning, not a static infinity, but a dynamic history. Scientists needed a mathematical structure to describe this. Albert Einstein had already developed equations that describe gravity as the curvature of space-time. His equations predicted a universe that should either contract or expand. Einstein did not like that prediction. He assumed the universe was static. To force the equations into a steady state, he added a term he called the cosmological constant. It acted as a kind of balancing pressure. Years later, after Hubble revealed the expansion of the universe, Einstein admitted that adding this constant to force a static universe was the greatest mistake of his career. His own equations had already pointed to the truth. Space must evolve. Once expansion became accepted, scientists could begin to explore what it implied. If the universe was smaller in the past, it must have been hotter. When a gas is compressed, it heats up. When space itself was compressed into a smaller volume, the energy and matter within it were intensely hot. The universe was once a furnace of unimaginable density. When it expanded, it cooled. Matter began to form. Atoms emerged. The cosmos went through childhood, adolescence, and maturity. But Hubble did not settle for a broad idea. He insisted on numbers. His results showed a direct relation between distance and speed. He could write the pattern as a constant rate of expansion. Even though we avoid symbols here in narration, the concept is simple. For every unit of distance, there is a predictable increase in speed. It is a speed of separation per distance of space. The more distant a galaxy is, the faster it moves away. At this stage, many scientists hoped there was some alternative explanation. Perhaps the redshift was caused by light losing energy over distance. Perhaps it was an artifact of the telescope. Perhaps the universe was not really expanding, but simply giving the illusion of motion. Science allows doubt. Science encourages doubt. Doubt is not a weakness. Doubt is the engine of discovery. Then better instruments were built. Measurements grew more precise. More galaxies were observed. The pattern did not weaken. It strengthened. Every refinement of technology confirmed the expansion. Doubt had been invited to challenge the result. Instead, doubt left the room. Many people imagine expansion like an explosion from a central point. That is not what is happening. Space itself is stretching. The galaxies are not flying through space. The space between galaxies is increasing. If two galaxies begin 1 billion light-years apart and space expands, they become farther apart without either galaxy moving through space. They follow the stretching pattern of space-time. The galaxies are passengers. Space is the vehicle. This is the part that feels impossible. How can empty space grow? On Earth, growth is connected to matter. A tree grows because it has atoms. A building expands by adding bricks. But space does not need matter to expand. Space is not a thing that has to be filled. It is a dynamic background influenced by energy. When energy density exists, space-time responds. General relativity explains that matter tells space-time how to curve, and space-time tells matter how to move. Expansion is the universe following its own rules. By the time Hubble presented his results, the idea of an unchanging universe no longer matched observation. The universe moves. The universe evolves. The universe has a past. Cosmology became a historical science. Each observation pushed us deeper into the past, closer to the beginning. The expansion of the universe is the first pillar of modern cosmology. Without it, there is no cosmic timeline. Without it, there is no reason to expect a hot beginning. Without it, there is no path toward understanding the relic radiation that fills all of space. Expansion is not a theory. It is a measurement written in the light of distant galaxies. At first, the idea that space itself could expand felt impossible. We are accustomed to motion through space, not the motion of space. When we watch a car drive down a road, we expect the car to move while the road remains fixed. Expansion reverses this intuition. Galaxies behave like cars that remain still while the road stretches underneath them. To most people, this sounds like a trick of language, a clever way to hide the fact that galaxies might simply be drifting through space. But measurements revealed otherwise. The galaxies are not rushing outward like fragments from an explosion. Their positions remain locally stable, while the fabric of space increases in size. Imagine a sheet of rubber marked with dots. The dots represent galaxies. If you stretch the sheet, every dot moves away from every other dot, yet none of the dots crawl across the surface. They simply follow the stretching of the sheet. Space behaves as the sheet. The galaxies behave as the dots. They are not racing through the universe. They are carried by the expansion of the universe. This discovery changed everything. It forced scientists to ask questions that no one had considered before. If space can stretch, can it shrink? Could space stop expanding? Could it reverse? Could space someday collapse back into a dense state? Every possibility had to be examined. Every possibility required a kind of thinking that had never been demanded before. To answer these questions, scientists returned to the equations of general relativity. Those equations describe how matter and energy influence the shape of space, and how the shape of space guides the motion of matter. It is a dance that never breaks rhythm. Einstein had once adjusted his equations to maintain a static universe because he believed stillness was the natural state. The discovery of expansion revealed that stillness was the illusion and motion was the truth. Astronomers continued measuring redshift and distance across larger volumes of space. The pattern held with astonishing clarity. The farther a galaxy was, the faster it receded. The relationship between distance and recession speed is known today as the Hubble-Lemaitre law. We speak the rule instead of writing a symbol. The speed of separation equals a constant multiplied by distance. Distance rises, speed rises. Simple, relentless, inescapable. Observations came from every direction. If our galaxy were in a unique place, expansion would look lopsided. In that case, galaxies in one direction would appear to move away faster than those in another direction. But the redshifts were consistent everywhere. No matter where astronomers pointed their telescopes, they observed the same trend. This was one of the most profound lessons cosmology ever provided. The universe does not revolve around us. Our position is ordinary. What we see is not a special perspective. It is what any observer in any galaxy anywhere in the universe would see. Every galaxy observes every other galaxy moving away. Expansion looks the same from all viewpoints because it happens to space itself, not inside space. Many people wondered if the redshift could have some other cause. Perhaps light simply loses energy while traveling long distances. But this idea fails a crucial requirement. If light lost energy in that gradual way, the loss would not maintain a precise relationship with distance. Some light would lose more energy, some less. The redshift would vary with no clear rule. Instead, the redshift follows an exact pattern. The rule exists because the cause is not random. The cause is the expansion of space. As more data arrived, cosmologists began to treat expansion not as a possibility, but as a fundamental property of the universe. Expansion became the first pillar of modern cosmology. A pillar is not a guess. A pillar is something that supports every other conclusion. Without expansion, there would be no reason to believe that the universe was once hot. Without expansion, there would be no prediction of a relic radiation filling space. Without expansion, cosmology could not exist. Once scientists accepted that space expands, a new question took hold. How fast does it expand today? The answer required extremely careful measurements. Astronomers refined distance indicators. They identified more galaxies. They compared results from different techniques. The value that describes the rate of expansion is called the Hubble constant, even though we avoid symbols here. The idea of a constant suggests something permanent, but the constant measures the present rate of change. It may not have been the same in the past, and it may not be the same in the future. For now, it tells us how rapidly galaxies separate at a given distance. The rate is expressed as speed per unit distance. Every additional distance causes an additional recession speed. If two galaxies are twice as far apart, their separation speed is twice as large. If they are 10 times as far apart, their separation speed is 10 times as large. This proportional relation is a signature of a deeper truth. The scale of the universe is growing. The distances between objects are increasing. The universe is not a static stage, it is an evolving entity. One of the most surprising consequences of expansion is that distant galaxies can appear to move away faster than the speed of light. People sometimes misunderstand this and wonder if galaxies are somehow breaking the ultimate speed limit of the cosmos. They are not. Nothing is moving faster than light through space. Space itself is expanding. The limit that applies to motion through space does not restrict the expansion of space. The speed of light is a speed within the universe. Expansion is a change in the structure of the universe itself. The difference is subtle and powerful. It changed our understanding of what motion means. As the idea of expansion took hold, scientists began tracing its consequences backward through time. The further we travel into the past, the smaller the universe becomes. Eventually, the volume of space shrinks to a state of unimaginable density and heat. In such a state, atoms cannot exist. Protons and electrons cannot bind. Before that moment, matter itself cannot maintain structure. There is a limit beyond which our physical understanding reaches a boundary. At that boundary lies the beginning of the observable universe. The beginning was not discovered through speculation. It was forced upon us by measurement. Expansion demanded that space was once smaller. General relativity demanded that smaller space was hotter and denser. The combination demanded that the universe had a beginning. The idea became inevitable. Expansion did more than reveal the past. It also pointed toward the future. If expansion continues forever, galaxies will drift farther apart, stars will burn their fuel, and the night sky will grow darker. In the far future, galaxies beyond our own cluster will slip beyond the horizon of visible space. The universe will become a lonely place. The grandchildren of galaxies will live in a cosmos where the evidence for expansion is gone. Future observers may never know that the universe once teemed with galaxies. They may never see what we see now. For that reason, we live in a fortunate moment. We are alive at a time when the sky is full of proof. We can still see the pattern that space draws. We can still measure the stretching of light. We can still trace the history of the universe to its earliest visible moment. The expansion of the universe is not simply a scientific conclusion, it is a gift of timing. There is a quiet irony in all of this. We once believed the universe was eternal because it looked eternal from our small place in space. Only when we learned how to measure the light from distant galaxies did we discover that the appearance of stillness was an illusion. The universe has always been moving. We were the ones who stood still. The confirmation of expansion was only the beginning. Once space was understood to be growing, curiosity pushed the next question into the center of every scientific discussion. If galaxies are moving away today, what happened yesterday? And the day before that? What did the universe look like when everything was closer together? What did it look like when matter was compressed into a far smaller volume? A single measurement of light began a chain reaction that led to one of the deepest transformations in human knowledge. Expansion forced a timeline. A timeline forced a history. A history forced the realization that the universe had a beginning. At first, the idea of a beginning felt uncomfortable. Many scientists preferred an eternal universe, not because evidence supported it, but because eternity felt simpler. A universe without a beginning needed no explanation. It simply existed. But expansion destroyed that comfort. As we trace expansion backward in time, space shrinks. When space shrinks, density rises. When density rises, temperature rises. And if we continue this reasoning far enough, we reach a moment when the universe was so dense and so hot that matter as we know it could not exist. This conclusion did not come from philosophy. It came from the logic of measurement. Imagine pressing a spring. You can compress it to a point, and when released, it expands. Now imagine compressing a spring until the coils merge into a single point. That point cannot compress further. Every earlier moment is contained within that point. That is what expansion reveals. The universe was once compressed into a state beyond our ability to visualize. We call that moment the beginning, not because we understand everything about it, but because the mathematics and the evidence leave us no other choice. This new understanding required scientists to think differently about time. For countless generations, humans believed that time stretched infinitely into the past. Then, expansion showed that time and space are connected. If space has a beginning, then time has a beginning. The universe is not a stage upon which events unfold. It is the event itself. Space, time, matter, light, and energy all began together. Nothing existed before because before is a word defined by time, and time began with the universe. This is not poetry. It is what the evidence demands. Once expansion became widely accepted, scientists looked for more proof. They searched for further signals in the cosmos that could reveal the early universe. One prediction stood out. If the universe was once hot, then the glow of that heat should remain somewhere. As space expands, light stretches. What was once blazing heat in the early universe should now be chilled to a faint whisper, a silent afterglow filling the universe in every direction, not tied to any star, not emitted by any galaxy, a relic of the beginning. The search began. Instruments were pointed at the sky. Radio antennas scanned the heavens. Years passed. Nothing conclusive was found. Then two engineers, working not in cosmology but in communication research, pointed a microwave receiver at the sky. They detected a faint hiss. It was present day and night. It did not point to any direction. It did not fluctuate. No matter where the antenna pointed, the signal remained. The engineers searched for problems. They cleaned the antenna. They removed nesting birds and debris. They even repaired parts of the receiver. The hiss did not disappear. They had discovered the relic glow predicted by the logic of expansion. That glow is called the cosmic microwave background. It is the oldest light we can see. It comes from a time when the universe was only a few 100,000 years old. Before that time, the universe was too hot for atoms to form. Particles of matter and light collided constantly, scattering light in every direction. The universe was fog. When the fog lifted, light escaped. That light has been traveling ever since. As space expanded, the light stretched into microwave wavelengths. We are not observing a photograph taken later. We are observing the actual light from that ancient moment. Later satellites created detailed maps of this ancient glow. The maps revealed that the temperature of the cosmic microwave background is 2.725 Kelvin, almost perfectly uniform, yet not entirely. There are tiny variations in temperature, differences smaller than 1 part in many 10,000s. These tiny differences correspond to regions with slightly more matter and slightly less matter. Over billions of years, the regions with more matter became galaxies. The regions with less matter became empty voids. Expansion did not simply stretch space, it allowed structure to emerge. These tiny variations were not noise, they were music. They were the frozen echoes of sound waves that traveled through the early universe like ripples in a cosmic ocean. When atoms formed and the fog lifted, those ripples became permanent. They remain imprinted in the cosmic microwave background. The universe has memory. As measurements improved, something new emerged from the data. The patterns of variation in the cosmic microwave background revealed the geometry of space itself. Space could be positively curved like the surface of a sphere. It could be negatively curved like a saddle. Or it could be flat. The measurements revealed a stunning truth. The universe is flat to an extraordinary precision. Not nearly flat, not approximately flat, measurably flat. The geometry of the universe follows the rules of simple triangles. Parallel lines remain parallel. the angles of a triangle add exactly as they do on a sheet of paper. This precision raised a deeper question. How could the universe be balanced so perfectly? If the density of matter and energy had been slightly greater, gravity would have caused the universe to collapse long ago. If the density had been slightly less, expansion would have ripped matter apart, preventing galaxies and stars and planets from forming. Instead, the universe balanced on the edge, not because of us, not so that we could exist. It simply did. Cosmology does not hide wonder. It only refuses to replace wonder with invention. Every discovery led to another. When scientists measured how stars move around the centers of galaxies, they found that the outer stars move too fast. If only visible matter existed, the galaxies would fly apart. Instead, something invisible holds them together. We call this dark matter. We cannot see it. We cannot touch it. But we measure its gravity. Without dark matter, galaxies cannot form. Without dark matter, stars cannot gather. Without dark matter, the universe would be light without structure. Then came the greatest surprise. Scientists measured distant, exploding stars that act as cosmic distance markers. When they calculated how fast the universe expands over time, they expected expansion to slow because gravity pulls galaxies toward one another. Instead, expansion is speeding up. Something is pushing space apart. We call this dark energy. Dark matter pulls. Dark energy pushes. The universe is shaped by a balance of forces we can measure, but do not yet fully understand. All of this insight, from expansion to dark energy, emerged from one bold conclusion. Space grows. The universe expands. Galaxies drift because the fabric of space stretches. Expansion is the first observational pillar of cosmology. Without it, nothing else makes sense. Expansion tells us that the universe has a history. The cosmic microwave background confirms it. The distribution of matter explains its evolution. The acceleration of expansion shapes its future. We are the first generation in the history of Earth to understand that we live in a universe with a past and a future. We are the first to measure the expansion. We are the first to capture the afterglow of the beginning. The night sky is not a static tapestry. It is a living record. The discovery of expansion forced humanity to confront a truth that no earlier civilization had imagined. The universe has a history. If space grows, then space was smaller. If galaxies drift apart, then galaxies were once closer. The conclusion leads somewhere deep, to a moment when the universe was dense, bright, and unimaginably hot. Expansion pointed toward a beginning, but it did not show us that beginning. Cosmology needed more than a direction. It needed proof. If the early universe was hot, then that heat would not simply disappear. Light carries memory. Space stretches light, but never erases it. Somewhere in the universe, that ancient heat should still exist. Not as the fiery glare of creation, but as a cooled whisper, the afterglow of a younger cosmos. To find such a relic, scientists turned their attention to microwaves. Microwaves are a form of light, but with longer wavelengths than the light visible to our eyes. Human eyes detect a small sliver of the electromagnetic spectrum. Telescopes and detectors allow us to see beyond that sliver. If the universe once glowed like a furnace, then as space expanded over billions of years, that light would stretch until it cooled into microwave wavelengths. The early universe would leave behind a faint radiation that fills all of space. It should not come from stars. It should not come from galaxies. It should arrive equally from every direction. The universe itself would be the source. Years passed. Instruments improved. The search continued. Then something unexpected happened. Two engineers were experimenting with a large microwave antenna. They were not searching for relic radiation. They were working on satellite communication. Yet whenever they pointed their antenna at the sky, they detected a constant hiss. It was quiet, but persistent. It did not matter where they aimed the antenna. It did not matter what time of day or season. The hiss was always present. They assumed something nearby was generating the noise. They cleaned the equipment. They checked the wiring. They removed nesting birds from the receiver and cleaned away feathers and debris. Nothing changed. The hiss remained. What they found was not noise. It was the fossil light of the early universe. That faint glow is called the cosmic microwave background. It is the oldest light the universe allows us to see. Before this moment, the universe was not transparent. It was a swirling ocean of free electrons and protons. Light could not travel freely because it was scattered in every direction by charged particles. Imagine fog so thick that a lamp cannot shine through. That was the early universe, a fog of pure energy and matter. As the universe expanded, it cooled. After roughly a few 100,000 years, the temperature dropped low enough for protons and electrons to combine into neutral atoms. When they combined, the fog lifted. Light was freed. That first free light is still moving through the cosmos. It has been traveling across the universe for more than 13 billion years. When we detect the cosmic microwave background, we are not looking at a photograph of the past. We are seeing the past itself. The temperature of this ancient light today is incredibly low. It measures 2.725 Kelvin. Kelvin is a scale beginning at absolute zero, where all motion stops. 2.725 Kelvin is only a few degrees above that perfect stillness. If you could place a thermometer in the emptiest region of space, far from every galaxy, the temperature you would read is the temperature of the cosmic microwave background. This is not an estimate. Satellites have mapped the entire sky with precise detectors that measure temperature differences smaller than 1 part in many 10,000s. The radiation is astonishingly uniform. It arrives from every direction almost equally. It does not favor any location. That uniformity is a message. It tells us that the early universe was smooth, evenly distributed, and nearly featureless. The cosmos began as a simple place, but not perfectly simple. When satellites improved, scientists detected tiny fluctuations in the temperature of the cosmic microwave background. These variations are incredibly small. They are differences that are minimal compared to the overall temperature. Yet hidden inside those slight variations is the blueprint for everything that exists. Regions that were just a little warmer had just a little more energy. Regions that were just a little cooler had just a little more matter. Over billions of years, gravity pulled the matter in those slightly denser regions together. They became stars, galaxies, and galaxy clusters. The entire structure of the universe, the vast cosmic web of galaxies spanning billions of light years, grew out of those tiny ripples in the ancient light. These ripples are not random. They are the frozen remains of sound waves that once echoed through the young universe. In the early plasma-filled cosmos, light and matter behaved like a fluid. Pressure waves traveled through that fluid the same way sound travels through air. Where the plasma compressed, temperature rose. Where the plasma thinned, temperature fell. When atoms formed and the light escaped, these sound waves became permanently imprinted in the cosmic microwave background. The universe carries a record of its own first vibrations. The cosmic microwave background is not an artifact. It is not a symbolic hint. It is direct evidence. It confirms that the universe was once hot, dense, and filled with light. It confirms that atoms formed only after the cosmos expanded and cooled. It confirms that the large-scale structure we see today grew from microscopic fluctuations. It confirms the timeline implied by expansion. Without this ancient light, cosmology would be speculation. With it, cosmology becomes measurement. The discovery of the cosmic microwave background transformed the idea of a beginning from a possibility into certainty. Expansion may point toward a starting point, but the cosmic microwave background shows us that starting point. It is a relic older than galaxies, older than stars, older than time as we experience it. No telescope can see beyond it, because before that moment, the universe was opaque. The cosmic microwave background marks the earliest visible horizon of time. To detect the afterglow of creation is to witness the moment when light first traveled freely. The universe became visible to itself. When the cosmic microwave background was first mapped in detail, scientists expected a simple pattern. They imagined a sky that would appear mostly smooth, with perhaps a few weak variations scattered across it. What they found was far more informative and far more beautiful. The temperature of the ancient light is uniform across the sky, yet tiny differences appear, each one holding the memory of conditions in the early universe. Those small variations are not noise, they are information. The early universe did not begin with chaos. It began with structure hidden inside near perfect simplicity. To understand what those variations reveal, imagine a vast ocean made not of water, but of plasma. Plasma is a state of matter where atoms are not yet formed. Protons and electrons move freely, constantly colliding. Light cannot travel far in this ocean because each photon of light is scattered the moment it encounters a charged particle. The universe at this time was bright beyond anything we can imagine, yet that brightness was trapped inside itself. Light had no pathway. There were no atoms. There were no molecules. There was no transparency. Inside that plasma ocean, pressure waves formed naturally. Gravity pulled matter inward. Radiation pressure pushed outward. These two opposing forces created vibrations. The early universe behaved like a musical instrument. The plasma rang with ancient sounds. We cannot hear them because sound requires air, and the universe contains no air. Yet these vibrations compressed and rarefied the plasma the same way sound compresses and rarefies air. When the universe cooled enough for atoms to form, the vibrations stopped. Atoms captured electrons. Light escaped. The pattern of these frozen pressure waves was etched into the newborn light. It is almost impossible to exaggerate how precise this information is. The pattern in the cosmic microwave background reveals the total amount of matter in the universe. It reveals how much of that matter is ordinary matter, the kind that forms atoms and stars and planets. It also reveals how much is dark matter, the invisible mass that shapes the universe through its gravity. The pattern even reveals the geometry of space. The exact size of the variations depends on the shape of the cosmos. If space were positively curved like the surface of a sphere, the variations would appear larger. If space were negatively curved like a saddle shape, the variations would appear smaller. When scientists analyzed the data, they found that space is flat, not approximately flat, measurably flat. The angles of the universe do not bend. Parallel lines remain parallel. This means that the total amount of matter and energy in the universe is balanced with astonishing precision. If there had been slightly more matter in the beginning, gravity would have pulled everything inward, collapsing the universe long before stars, planets, or life could emerge. If there had been slightly less matter, the expansion would have been too rapid. Galaxies would not have formed. Stars would not ignite. There would be no place for atoms to gather into worlds. Instead, the universe walked a perfect line. It is balanced on a razor of possibility. The cosmic microwave background proved that the universe began in a hot, dense state, expanded, cooled, and then allowed atoms to form. But that was not the end of what it revealed. Scientists learned that the universe was born with small imperfections. These imperfections are not flaws. They are seeds. Every galaxy that exists today began as a tiny region of slightly greater density in the early universe. Without those imperfections, the cosmos would be smooth, an empty fog of matter forever drifting apart. Nothing would form. No star would ignite. No planet would orbit. No life would emerge. The cosmic microwave background shows us that the universe began with exactly the right level of imperfection. Not too chaotic, not too smooth. Just enough variation for gravity to shape structure over billions of years. When satellites mapped the sky, something else became clear. The The cosmic microwave background arrives from every direction. It does not point to a center. It does not reveal a preferred location. This tells us something profound. The universe does not have a special place. We are not at the center. There is no center. The expansion of space happens everywhere. Every point in space observes the same pattern. If civilizations exist in distant galaxies, they would measure the same ancient light, see the same variations, and reach the same conclusions. Cosmology is universal. Even more astonishing is that this relic light has been cooling for more than 13 billion years, yet it still blankets the universe. It has stretched from searing heat to faint whispers of microwaves. Light never stops traveling unless something stops it. Nothing in the vast majority of space stopped this ancient light. It crossed the expanding universe unchanged, except for the stretching caused by space itself. When you stand under the night sky, that ancient light washes over you. It passes across your skin. It flows through your body. You are immersed in the memory of the universe without even knowing it. To detect something so faint seems impossible. Yet science found a way. First came a microwave antenna on Earth, then satellites in orbit above the atmosphere. Each new instrument sharpened the picture. The first full sky map revealed only the presence of the ancient radiation. The second map revealed the variations. Later maps revealed the fine structure of the variations. With each improvement, the universe became clearer. The ancient light is not a mystery. It is data, cold and precise. It tells us the temperature. It tells us the density. It tells us the composition of matter. It tells us the age of the universe. From this single piece of evidence, we learn that the universe is roughly 13,800 million years old. Not because someone guessed, because the cosmic microwave background tells us how long light has been traveling. It gives us a timestamp carved into the sky. The ancient light confirms that the universe has a beginning, not a philosophical beginning, a measurable beginning. It confirms that matter formed in stages, first particles, then atoms, then stars, then galaxies, then planets. It confirms that the universe was once simple, then gradually grew complex. The relic light proves that we are not living in a static eternal cosmos. We are living in a universe that evolves. The cosmic microwave background is a message from childhood. It tells us where everything started. It tells us that the universe remembers. In every field of science, there is a moment when doubt turns into certainty. For cosmology, that moment arrived when the cosmic microwave background was measured with enough precision to reveal not just its temperature, not just its presence, but its fingerprints. Those fingerprints are patterns of tiny variations across the sky, and they match exactly what a hot, expanding universe predicts. If the early universe had been static or eternal, if it had not expanded and cooled, if atoms had always existed, then the sky would not contain this ancient light. There would be no relic radiation. There would be no map of primordial variations. The cosmic microwave background is the universe itself verifying the expansion. Scientists built more advanced instruments to study the ancient light from above the atmosphere, where Earth could not interfere. The first satellite map revealed the cosmic microwave background with coarse detail. It confirmed that the relic glow existed everywhere. Later satellites produced sharper images. With each new generation of technology, the picture moved closer to perfection, like adjusting a focus knob on a telescope that reveals finer patterns each time you touch it. The variations across the sky form a pattern that resembles a mottled texture. Each tiny patch represents a place where the density of the early universe was slightly higher or lower than average. The differences are incredibly small, yet these tiny differences are enough to grow entire galaxies. Over billions of years, gravity turned faint ripples into grand structures. In some regions, matter collected and collapsed. In other regions, matter flowed outward, leaving behind emptiness. What began as faint ripples became the cosmic web. The cosmic web is a vast structure made of galaxies arranged in filaments that stretch across space like strands of silk. These filaments are separated by enormous empty regions called voids. The web is not random. It is the natural result of gravity acting over billions of years on the small initial variations recorded in the cosmic microwave background. When we compare computer simulations of the universe with actual galaxy surveys, the resemblance is astonishing. The map of the cosmic microwave background already contains the pattern of the future. The cosmic microwave background is more than evidence, it is prophecy fulfilled. It shows the seeds at the beginning, and we watch those seeds grow into galaxies exactly as predicted. Yet the ancient light reveals something even more subtle. It contains slight differences in temperature that form peaks and valleys when plotted across different scales. These peaks correspond to the scale of sound waves in the early universe. The clarity of these peaks tells us how much matter exists. It tells us how much of that matter is normal matter. It tells us how much is dark matter. It even tells us the age of the universe with remarkable accuracy. The ancient light is the universe reading out its own settings, like a machine printing its internal configuration. With this knowledge, cosmologists learned that the universe is made mostly of what we cannot see. Ordinary matter, the kind that forms atoms and stars and planets and life, makes up only a small fraction of everything. Dark matter outweighs normal matter many times over. And dark energy, the force that accelerates the expansion of space, outweighs both. The ancient light reveals this balance. Normal matter forms stars. Dark matter shapes galaxies. Dark energy shapes the future. Each of these revelations came from measuring the temperature of a faint glow that fills the sky. The existence of this ancient radiation also erases the last argument against a dynamic universe. Before its discovery, some scientists believed light might shift to red, not because of expansion, but because it gradually lost energy during travel. But if that theory were true, the universe would not contain the cosmic microwave background with its exact temperature and pattern. There would be no reason for the brightness to be uniform. There would be no explanation for the fine details that encode matter density, geometry, and age. The cosmic microwave background rejects every alternative explanation. Only a universe that began hot and expanded into the universe we observe today can produce this ancient light. When we look at the cosmic microwave background, we are not seeing through space, we are seeing back through time. The light we detect was emitted when the universe was incredibly young. Before that moment, the universe was opaque. We cannot observe anything earlier with light. That moment forms a horizon. It is a wall of time that light cannot cross. We call it the surface of last scattering, not a physical surface with edges or texture, but a moment in time when the fog cleared. Standing beneath the night sky, we see stars that are nearby within our own galaxy. Beyond those stars lie other galaxies, scattered across vast distances. Beyond those galaxies lies the cosmic microwave background, a wall of ancient light marking the farthest boundary of what we can observe. We will never see farther with light because there was no light before atoms formed. The universe keeps its earliest moments hidden from sight, but the ancient light reveals almost everything else. It shows that the universe began hot. It shows that the universe expanded. It shows that the universe cooled. It shows that atoms formed. It shows where galaxies would eventually grow. Even the idea that the universe is flat and balanced with miraculous precision comes from the pattern embedded in the ancient light. We can measure the largest sound wave that formed in the early universe. We can measure the angular size of that sound wave as it appears today. That measurement only makes sense if space is flat. If the universe had a different shape, the size of that peak would not match observation. Flat space means that the total energy of the universe is balanced. The gravitational pull of matter and the push of expansion nearly cancel. If the universe had slightly more matter, it would have collapsed. If it had slightly less matter, The expansion would have torn everything apart before galaxies formed. The universe sits at a balance point so narrow it feels unreal. Yet the evidence shows it is true. The cosmic microwave background proves that the universe is not random. It is not a chaotic accident. The universe follows rules, and those rules are written into the sky. The ancient light teaches us a final lesson. The universe does not care whether the truth is comfortable. The universe does not care what we expect. The universe cares only about what is. For thousands of years, humans believed that the heavens were perfect, unchanging, eternal. Then a faint whisper in microwave light revealed that the heavens had a childhood. Space grew, matter formed, light escaped. The universe did not begin with darkness, it began with light. In the earliest moments after the universe began, nothing existed that we would recognize. No atoms, no molecules, no stars, no galaxies. Not even light could travel freely. Time and space had only just unfolded from the dense beginning revealed by expansion and the ancient light. The universe was pure energy. Everything that would ever exist was contained in an ocean of particles so hot that even the concept of matter was unstable. Yet within this fiery beginning, something remarkable happened. The first ingredients of reality formed. They formed not through chance or luck, but through the unavoidable laws of physics. Cosmology tells the story of how simple particles became the building blocks of everything. Hydrogen, helium, a trace of deuterium, a faint whisper of lithium. Nothing more, nothing less. The early universe made exactly the elements that its temperature and density allowed. The universe performed its first and most elegant experiment. In the first fraction of a second after the beginning, the temperature of the universe was so high that particles existed only as a storm of energy. Space expanded rapidly. As space expanded, temperature decreased. Expansion is cooling. At the very earliest times, the energy was great enough to create matter and antimatter in equal amounts. Particles collided and annihilated. Some matter survived. Every atom in your body comes from that tiny imbalance. As the universe continued to expand, particles slowed enough to combine into simple building blocks. First came protons and neutrons. These are formed from smaller particles bound by the strong nuclear force, the force that holds atomic nuclei together. In the early universe, protons and neutrons collided constantly, trying to bind together into heavier combinations. But the temperature remained too high. Any nucleus that formed was almost immediately torn apart by the intense energy around it. Imagine trying to build a sandcastle in the middle of a storm. Every grain you place is swept away by the chaotic wind. That was the state of the universe during its newborn moments. Protons and neutrons attempted to link, only to be torn apart again and again. The universe had to wait. It had to cool. Only after the temperature fell to a specific range could nuclear binding outpace the destruction from energy. This happened when the universe was roughly 1 second old. Not 1 minute, 1 second. At that moment, the temperature had dropped to a range in which protons and neutrons could finally hold together for more than an instant. The first stable nucleus that could form in this new environment was deuterium. Deuterium is a heavy form of hydrogen. It contains 1 proton and 1 neutron. Forming deuterium was the first victory over the intense energy of the early universe. But the victory was fragile. Deuterium could exist, yet the temperature was still high enough to destroy it in collisions. For a brief time, formation and destruction competed. Nuclei appeared and vanished like foam at the edge of a stormy ocean. Then, as more seconds passed and the universe cooled further, deuterium became stable enough to survive long enough for something more to happen. 2 deuterium nuclei could fuse to make helium. A nucleus of helium contains 2 protons and 2 neutrons. In the brief window before the universe cooled too much to allow fusion, nearly every available proton and neutron found their way into either hydrogen or helium. Hydrogen ended up dominating because there were more protons than neutrons. Helium formed from those protons that could capture neutrons through nuclear reactions. The amount of time when fusion could occur in the early universe was incredibly short. In a few minutes, the temperature dropped low enough that nuclear fusion stopped completely. From that moment on, the universe held its first permanent recipe of elements. The ratios were precise: about 3/4 hydrogen, about 1/4 helium, a small trace of deuterium, a faint hint of lithium. Those ratios are not approximations. They are measured today, and they match predictions calculated from the physics of the early universe. This is the second great proof of cosmology. Expansion tells us the universe had a beginning. The cosmic microwave background tells us the universe was once hot and filled with light. Primordial element abundances tell us what that early heat produced. The ratios are astonishingly exact. The universe contains roughly 75% hydrogen by mass and roughly 25% helium by mass. Not 60% and not 30%, not 90% and not 10%. The prediction comes directly from the laws governing nuclear fusion at specific temperatures and densities. The prediction was made long before measurements were precise enough to confirm it. Then astronomers turned their instruments to the oldest stars, the most untouched regions of gas, and distant galaxies so young that stars had barely begun to change the chemistry of the universe. Everywhere they looked, the numbers matched. Hydrogen and helium appear in the exact proportions predicted by a universe that formed these elements in its very first minutes. This success cannot be explained by coincidence. Hydrogen and helium form in these exact ratios only under conditions that match the early universe. If the density had been significantly higher or lower, the ratios would be different. If the expansion rate had been faster or slower, the ratios would be different. If the laws of physics were even slightly different, the ratios would be different. Primordial element abundances tell us that the universe passed through a narrow window of temperature and density. When that window closed, the fusion stopped. Nothing that happened afterward in stars or galaxies changed the primordial helium fraction enough to erase this signature. The universe preserved its original chemistry as a fossil record. Stars do produce helium through fusion in their cores, but they do not produce the overwhelming proportion of helium observed throughout the cosmos. Stars also produce heavier elements like carbon, oxygen, and iron. These elements build planets and life. But the abundance of helium far exceeds what stars can make. The universe began with helium already present. This discovery shattered the idea that stars could build all the elements in the universe from hydrogen alone. The helium existed first. Stars inherited it. To understand why these primordial abundances are so powerful as evidence, consider an analogy. Imagine finding a loaf of bread. You analyze its chemical composition and find that it contains exactly the right ratio of ingredients to match the recipe for sourdough bread. You know, without seeing the baker, that specific steps were followed at specific times. Primordial abundances are the recipe of the universe. They prove that the universe must have passed through particular temperatures and densities at particular times. They prove that the early universe was hot enough for nuclear fusion, yet cooled quickly enough to freeze the results in place. Only a universe that began dense and expanded rapidly could produce these exact ratios. Deuterium plays an especially important role. Hydrogen and helium might be explained in imaginative ways if one ignores the evidence, but deuterium cannot. Deuterium forms only under specific conditions. If the early universe had been too dense or too hot for too long, deuterium would have been completely destroyed. If it had been too cool, deuterium would not have formed at all. The amount of deuterium present today is a direct and sensitive indicator of the conditions in the first few minutes. We measure its abundance in distant gas clouds that have never been processed inside stars. The fraction we observe matches the predictions so precisely that there is only one conclusion to draw. The early universe had exactly the temperature, density, and expansion rate predicted by the hot, dense beginning. No alternative idea ever proposed can explain primordial abundances. A steady, eternal universe cannot produce helium and deuterium. in these specific proportions. Stellar processes cannot create these ratios because stars produce different mixes depending on their mass and lifetime. Chemical reactions cannot produce them. Random chance cannot produce them. Only the hot beginning does. When we place primordial element abundances beside expansion and the cosmic microwave background, the story becomes undeniable. Expansion shows that the universe had a past. The cosmic microwave background shows us that past, filled with light. Primordial abundances show us what that early light created. Each line of evidence supports the others. Together they form a structure that cannot be broken. Cosmology becomes not a theory about the universe, but a measurement of the universe. The most poetic truth of all is that the hydrogen in every drop of water in your body was forged in the first few minutes of time. The helium in every red balloon began as the ash of the universe itself. Every star that shines is burning the hydrogen left over from the beginning. The first chemistry of the universe is not distant. It is within you. Every breath you take contains atoms older than stars. You carry the memory of the universe inside you. The first elements were made when the universe was only minutes old. They became the raw material for stars. Stars built heavier elements. Those heavier elements became planets. Planets became places where life could emerge. From the simplest particles to the complex web of consciousness, everything traces back to those first minutes. When we hold a glass of water, we are holding the ashes of creation. In those minutes after time began, the universe wrote its first chapter in a language of hydrogen and helium. It produced exactly what its laws allowed. Not because it wanted to, not because it had purpose, but because the laws of physics shaped the unfolding of space and time. Before humans built telescopes powerful enough to reach beyond our galaxy, the universe appeared scattered and empty. Stars shimmered in isolation. Space looked like a silent field of light surrounded by darkness. We saw points, not patterns. We imagined distance, not structure. Our senses whispered that everything was random. But the universe does not obey the human intuition. It obeys gravity. And gravity is patient beyond imagining. When astronomers finally mapped thousands upon thousands of galaxies across enormous distances, something unexpected emerged from the data. The galaxies were not scattered like sand. They formed a structure that stretched across the universe. It became known as the cosmic web, a structure so vast that it challenged every assumption humans held about emptiness. Imagine looking at a grain of pollen under a microscope. Something that first appears simple and smooth reveals geometry, valleys, ridges, and symmetry. Our view of the universe went through the same transformation. When we looked deeper, structure appeared. Galaxies gathered into families. Families gathered into clusters. Clusters linked into filaments that stretch across hundreds of millions of light years. Between the filaments lie enormous empty regions called voids. Inside the filaments are chains of galaxies pulled together by gravity. The universe resembles a vast three-dimensional tapestry. Where the threads cross, galaxy clusters form. Where the threads thin, galaxies stand alone. Where the threads vanish, emptiness reigns. The cosmic web is the largest pattern humans have ever seen. Not a metaphor, not an artistic expression. A measurable structure. We do not infer it. We map it. Observatories scan the sky for redshifts, recording how far away galaxies are by the way their light has been stretched as space expands. Each galaxy becomes a point of data. When millions of points are plotted in 3 dimensions, the image is breathtaking. The universe is not a cloud of galaxies. It is a network, a skeleton of structure shaped by gravity. But gravity alone does not explain what we see. If only the visible matter that forms stars and planets existed, the cosmic web could not have formed. There is not enough mass. Galaxies would not have gathered into filaments. Clusters would not have pulled together. the web would never have emerged. Something else had to exist. Something invisible. Something with mass but no light. Something that does not interact with electromagnetic radiation. We call it dark matter. Dark not because it is mysterious, but because it does not radiate or reflect light. The existence of dark matter is not speculation. Its effects are measured. When scientists studied how stars move within galaxies, they discovered that the stars on the outer edges move much faster than expected. Normally, objects farther from the center of gravity move more slowly, the same way planets farther from the Sun take longer to complete their orbit. Yet the stars in the outer regions of galaxies move at nearly the same speed as the stars near the center. This can only happen if something massive surrounds the galaxy, something we cannot see. Dark matter. Gravitational lensing confirmed this. Light bends when it passes near mass. When astronomers studied distant galaxies behind clusters of galaxies, they discovered that the light from those distant galaxies was distorted more than visible matter could account for. Only an enormous halo of invisible mass could bend the light that much. Dark matter shaped the light. Space became a lens. The invisible became measurable. Then cosmologists tested the idea in the most direct way possible. They built enormous computer simulations. In these simulations, they placed matter into a virtual universe, allowed gravity to operate, and watched structure form over billions of years. When the simulations included only normal matter, the result was chaos. Galaxies formed too slowly. Clusters never developed. There was no web. But when they included dark matter, the simulation produced filaments, voids, and clusters that matched the real universe with astonishing accuracy. When the data and the simulation agree, misunderstanding becomes impossible. The cosmic web exists because dark matter shaped it. The most astonishing part is that the pattern of the cosmic web was already written in the tiny fluctuations of the ancient light from the cosmic microwave background. The same faint ripples that seeded future galaxies determined how dark matter would gather. The universe planted those seeds when it was only a few 100,000 years old. Over billions of years, gravity grew those seeds into the largest structure in existence. The cosmic web is not random. It is the result of matter responding to the mathematics of gravity. Everything familiar to us lives inside one filament of this web. Our galaxy is part of a structure called the local sheet. This sheet lies within a larger group of galaxies called the local group. That group lies along a filament that stretches across unimaginable distances toward a gigantic galaxy cluster called the Virgo cluster. The Virgo cluster is part of a still larger structure called the Laniakea supercluster, a vast river of galaxies flowing along gravitational pathways. Every galaxy in this river is drifting, drawn by gravity along the threads of the web. We are passengers on a cosmic current. The web reveals something about the universe that people rarely consider. Emptiness is not a lack of structure. Emptiness is a feature that defines structure. The voids are not mistakes. They are essential. They are the spaces into which matter flows as gravity shapes filaments. Without emptiness, nothing could cluster. Without emptiness, nothing could gather. The universe needs voids so that structure can exist. The cosmic web also reveals how slow and patient the universe is. Gravity works over billions of years. It never rushes. It never stops. It waits. And with enough time, small variations become enormous structures. What began as tiny differences in the ancient light grew into filaments that span billions of light years. The universe shows that complexity does not require planning. It requires time. Most of the mass in the universe belongs to dark matter. Visible matter is only a thin frosting on the surface of a far larger invisible structure. When we look at the night sky, we do not see the true form of the universe. We see only its highlight. Cosmology allows us to reveal the skeleton underneath. The cosmic web is the bone structure of the universe. This idea changes how we view ourselves. The galaxies that hold stars, planets, and life are not scattered like dust. They are part of a colossal network. Each of us occupies a node on that network. We live not in isolation, but inside structure. The universe did not simply expand, it organized. The cosmic web is a record of how the universe grew. It is the product of gravity pulling matter toward matter. It is the signature of dark matter, shaping space in silence. It is the final proof that the universe evolves from simplicity to complexity. Cosmology does not describe randomness. Cosmology describes emergence. We began by believing the universe was empty. Then we learned the universe was expanding. Then we discovered that ancient light filled all space. Now we see the structure that light predicted. When we study the cosmic web, we are seeing the universe reveal its architecture. For most of human history, we believed that everything important could be seen. Light guided our understanding. What we could not see, we ignored. Stars were points, planets were wanderers, space was emptiness. We built a model of the universe from what our eyes could gather. Then telescopes expanded our vision and revealed galaxies beyond counting. Yet even that was only the beginning. With time, astronomers reached a discovery that shattered our oldest intuition. Most of the universe is invisible. It is not empty. It is full of matter that does not emit light, does not reflect it, and does not absorb it. We cannot feel it or touch it, yet it shapes everything. To understand this invisible presence, we begin with the motion of stars within a galaxy. A galaxy is not a single solid body. It is a system of hundreds of billions of stars orbiting a common center. Gravity guides these orbits. Near the center of a galaxy, the gravitational pull is strong and stars move quickly. Farther out, where less mass is enclosed, the pull weakens and stars should move more slowly. Planets orbit the Sun the same way. Earth orbits more quickly than Jupiter. Jupiter orbits more quickly than Neptune. This pattern is universal for systems governed only by visible mass. But when astronomers measured how stars move within galaxies, they found something astonishing. The stars far from the center did not slow down. They moved just as fast as stars closer in. This was impossible if the only mass present was the mass we could see. Something else had to be there, something heavy, something spread throughout the galaxy, something that created a gravitational pull large enough to hold the fast-moving stars in place. Without that hidden mass, galaxies would fly apart. The discovery began with careful measurement, not speculation. Astronomers plotted rotation curves, graphs that show how the speed of stars changes with distance from the center. Instead of falling, the curves flattened. The stars behaved as though the galaxy were surrounded by a massive halo, a cloud of matter that extends far beyond the visible edge. This matter emits no light, yet it is heavier than everything that shines. We call it dark matter. Dark not because it is mysterious, but because it does not interact with light. The idea seemed radical at first. How could the universe contain enormous amounts of matter that no one could see? But observations kept piling up. The rotation curves of spiral galaxies all shared the same unexpected shape. The outer stars moved too quickly, and galaxies were not the only evidence. Clusters of galaxies also moved too fast. Gravity should have torn them apart. Something invisible held them together. The next confirmation came from gravitational lensing, the bending of light by mass. When light from a distant galaxy passes near a cluster of galaxies, the gravity of the cluster distorts the light. It acts like a lens. By measuring the distortion, astronomers can calculate the total mass of the cluster. Again, the visible mass was far too small. Something unseen was exerting most of the gravitational pull. The universe whispered its secret through the bending of light. Mass shapes space. Space shapes the path of light. Light reveals mass. When astronomers compared the visible mass to the total mass indicated by lensing, the result was overwhelming. Most of the mass was dark matter, but the most remarkable evidence came from watching entire clusters of galaxies collide. When two clusters pass through each other, the galaxies themselves behave like solid objects. They pass by with little direct interaction. Gas within the clusters behaves differently. It collides, heats, and slows down. Dark matter, however, does not collide like that. It passes straight through. In observations of these collisions, visible gas stops and lingers, but the mass revealed by gravitational lensing moves ahead. The mass is separate from the matter that emits light. Only dark matter fits the data. Cosmologists then carried the idea into immense computer simulations. They filled a simulated universe with matter, allowed gravity to act for billions of years, and watched. When they used only normal matter, the result was chaos. Galaxies formed slowly. No large structure emerged. There was no cosmic web. But when they added dark matter, the simulation created exactly what we observe in reality. Filaments, voids, clusters, a web of structure. The simulation becomes indistinguishable from maps of the actual universe. To understand how astonishing this is, imagine drawing a map of a city where you see only the lights in windows at night. No roads, no buildings, only dots of light. When you connect those dots with information you cannot see, you discover the true layout of the city. Dark matter is the cosmic version of that hidden structure. It connects galaxies the way invisible roads connect distant houses. We do not see dark matter directly. We see the universe move under its influence. Dark matter does not emit light. Dark matter does not reflect light. Dark matter does not absorb light. Yet dark matter sculpts the universe. It pulls galaxies into clusters. It holds stars in orbit. It shapes the cosmic web. Normal matter is a passenger. Dark matter is the driver. We might ask what dark matter is made of. Scientists do not yet know. It is not made of atoms. It passes through normal matter as if normal matter were mostly empty space, which it is. Every atom consists almost entirely of emptiness between the nucleus and the electrons. Dark matter does not interact with that structure. It only interacts through gravity. It behaves like a ghost that pulls everything but is felt by nothing. Several possibilities exist. Dark matter may be composed of particles that rarely interact with atoms. It may be something entirely new, a form of matter that existed from the earliest moments of the universe. It may be connected to symmetries in physics that are not yet fully understood. Whatever it is, dark matter reveals that our knowledge of matter is incomplete. The amount of dark matter is enormous. For every bit of normal matter we can see, there is roughly 5 times as much dark matter. If you gather all the stars, planets, and gas in the universe, dark matter still outweighs them. That means everything we can touch or see is only a small fraction of what exists. The structure of the universe makes sense only when we include dark matter. Galaxies form in regions where dark matter collects. Stars form inside galaxies. Planets form around stars. Life forms on planets. Without dark matter, there would be no galaxies. Without galaxies, there would be no stars. Without stars, there would be no life. Dark matter is not just an abstract idea, it is part of the story of existence. Dark matter created the scaffolding of the cosmos. It determined where galaxies would grow. It determined where voids would remain empty. When we look at the night sky, we see only the highlights of a deeper structure. We see the bright edges of an invisible architecture. Dark matter is the architect. We once believed that light revealed the truth. Now we know that the truth is deeper. Light reveals only what glows. Gravity reveals what exists. The invisible outweighs the visible. The unseen shapes the seen. And the universe is more than what our eyes allow us to witness. Dark matter forces a profound shift in perspective. Reality is not defined by appearance. Reality is defined by influence. Dark matter shapes the fate of galaxies. It shapes the fate of the universe. And it leaves us with a final thought. The greatest part of the cosmos is not what shines. It is what sculpts. For centuries, humans imagined the universe as steady and unchanging. Stars appeared fixed. Galaxies were unknown. Space itself was assumed to be a silent backdrop, unmoving and eternal. Then measurements revealed the expansion of space, and our understanding shifted. The universe was not static. It was growing. For decades, scientists believed gravity would gradually slow that expansion. After all, gravity pulls. If enough matter exists, eventually gravity should halt expansion and perhaps even reverse it. That expectation felt logical, elegant, comfortable. The universe would expand, slow, and perhaps collapse. Everything would end where it began. Then a discovery overturned that belief. Instead of slowing, the expansion of the universe is speeding up. Space is not only growing, it is accelerating. Something is pushing galaxies apart faster and faster. That something is called dark energy. Dark not because it is mysterious, but because it does not emit light. It does not reflect light. It does not absorb light. We do not see it directly. We see what it does. It pushes space itself to expand more rapidly with time. The discovery began with a question about the brightness of distant stellar explosions. These explosions are known as Type 1, a supernova. When a white dwarf star gathers too much material from a companion star, its mass reaches a limit. The internal pressure becomes overwhelming, and the star ignites in a runaway fusion event. The entire star explodes in a burst that momentarily shines as bright as an entire galaxy. Because these events all occur when the star reaches nearly the same mass. They all explode with almost the same brightness. That makes them perfect standard candles. If we know how bright an object truly is, and we measure how dim it appears, we can determine how far away it is. Type 1. A supernovae allow astronomers to map distances across billions of light years. Two teams of scientists began recording these distant explosions. They measured the expansion of the universe at different moments in cosmic history, like a time-lapse of space itself. They expected to find that distant supernova would show the universe slowing down in the past. Instead, the opposite was true. The supernova were dimmer than expected. They were farther away than they should have been if expansion was slowing. The only explanation was shocking. The expansion of the universe was accelerating. At first, the scientific community met this claim with skepticism. Extraordinary claims demand extraordinary evidence. The teams rechecked the data. They verified the brightness. They re-examined the calibration of their instruments. The acceleration remained. Other instruments and other observatories confirmed the result. It did not matter where scientists looked. The message was consistent. Space is accelerating. The idea felt impossible because we know of only one force that acts between galaxies on vast scales: gravity. Gravity pulls everything together. It does not push things apart. Yet something was acting opposite to gravity. Something with a pressure unlike anything known. The name dark energy was chosen to describe whatever causes this acceleration. Dark energy is not an object. It is a property of space itself. It fills the universe uniformly. It does not cluster. It does not form structures. It does not gather into galaxies or clouds. It simply pushes outward. This is not the first time such an idea was considered. When Einstein developed general relativity, his equations predicted an expanding or contracting universe. Einstein believed the universe was static, so he introduced a term into his equations to counter gravity and hold the universe still. This term is called the cosmological constant. Later, when expansion was discovered, he reportedly considered the constant his greatest mistake. Yet now it appears the constant may be real after all. The universe contains a form of energy associated with space. As space expands, more of that energy appears, and the expansion accelerates. The implications are staggering. Dark energy acts everywhere. It affects the entire universe equally. Even in the emptiest void, dark energy remains. It is not diluted as space expands. Instead, as space grows, the total amount of dark energy increases. Gravity becomes weaker with distance, but dark energy does not. There is no boundary where its influence stops. To understand how strange this is, imagine stretching a rubber sheet. If the sheet becomes larger, its material becomes thinner. But dark energy behaves as if the sheet gains new material as it stretches. The more space exists, the more dark energy exists, and the faster the expansion becomes. Nothing we experience in daily life behaves this way. The evidence for dark energy does not come only from supernova measurements. It appears in the cosmic microwave background, which carries the imprint of the early universe. The detailed variations in temperature tell astronomers how much matter and energy existed shortly after the beginning. The measurements show that the universe contains more energy than normal matter, and dark matter can account for. The missing energy must exist, and it must be in a form that does not collapse into structures, a form that pushes space apart. Another piece of evidence comes from the large-scale structure of the universe. The cosmic web is not simply a snapshot of galaxies. It is a fossil record of how gravity has shaped space over billions of years. The geometry of that structure reveals that something counteracts gravity. Without dark energy, the cosmic web would look different. Only one universe produces the pattern we observe, a universe with dark energy. Dark energy now dominates the fate of the cosmos. Long ago, matter dominated. Gravity shaped galaxies. Dark matter sculpted the web. But as space expanded, matter became more diluted. Dark energy, however, remained constant. In the present universe, most of the energy is dark energy. That means expansion is accelerating faster and faster. If this continues, the future will be lonely. Galaxies beyond our local region will move so far away that their light will never reach us. Space will expand faster than light can cross it. The night sky of distant future observers will become empty. Their entire observable universe will contain only the galaxies bound together by gravity in their immediate region. They will not see the cosmic web. They will not detect expansion. They will not observe the ancient light of the beginning. They will not know the truth. The universe will hide its own history. We exist in a brief moment when the sky is still filled with evidence, when we can still detect the ancient light, when we can still trace the expansion, when we can still measure the cosmic web. It is as if the universe allows us one cosmic generation to learn its story before the story fades from view. Dark energy challenges our understanding of physics. We do not know what it is. We know how it acts. It accelerates expansion. It behaves as if empty space contains energy. We search for clues in quantum physics, where empty space is not truly empty. We search in theories of gravity that extend beyond general relativity. Perhaps dark energy is connected to the energy of the vacuum. Perhaps it is a field that fills space. Perhaps it is something entirely unknown. Yet one fact stands above all. Dark energy is real. It is revealed not by belief, but by measurement. It shapes the future of the universe. It is the silent engine of cosmic acceleration. We once believed the universe was slowing. Now we know it is rushing toward an ever-expanding future. Dark matter shapes structure. Dark energy shapes destiny. Space looks flat to the human eye. We walk across the ground and see a horizon that seems perfectly straight. Our senses are tuned to small scales, the familiar scales of landscapes and cities. Even the entire planet looks flat when we stand upon it. Only when we step back, when we look from far above, when we measure instead of assume, does the true shape of something reveal itself. The same transformation happened to our understanding of the universe. At first, we assumed space was flat because it appeared that way. Then Einstein showed that mass curves space. Gravity is geometry. What we feel as force is the path that objects follow when space bends. We could imagine planets orbiting stars the same way marbles follow the slope of a bowl. Space is not a rigid grid. It is flexible. It bends. It stretches. It curves. Once we knew that mass and energy can curve space, a deeper question emerged. Not whether space is curved near stars, or black holes, but whether the entire universe has a shape. Is space flat like a sheet? Is it curved like the surface of a sphere? Is it shaped like a saddle, bending outward in one direction and inward in another? These are not poetic questions. They are measurable. They determine the fate of everything. The geometry of space reveals whether the universe will expand forever, slow and halt, collapse, or do something stranger still. In mathematics, shape is not defined by appearance. It is defined by behavior. On a flat surface, parallel lines never meet. On the surface of a sphere, parallel lines eventually intersect. On a saddle-shaped surface, parallel lines spread apart. The geometry of the universe decides which of these rules the cosmos obeys. If the universe is flat, then triangles drawn across vast distances have angles that add up to exactly 180 degrees. If space is curved like a sphere, the angles in that cosmic triangle add up to more than 180 degrees. If space is curved like a saddle, the angles add up to less. That simple test contains the entire question of cosmic geometry. But how do we draw a triangle the size of the universe? We cannot stretch tape measures between galaxies. We cannot walk across billions of light years. To measure a triangle, we need to know the true size of something and compare it to how large it appears. What we needed was a ruler that the universe itself provided. A ruler of known length located at the farthest observable distance. Something standard, something ancient, something that existed everywhere. The cosmic microwave background supplied that ruler. The ancient light contains ripples, the frozen remains of sound waves that moved through the early plasma. These ripples have a characteristic size. They form a preferred scale. If space were curved, that scale would appear larger or smaller when we observe it. If space is flat, that scale appears exactly as the geometry of normal Euclidean expectation predicts. In other words, nature placed a reference marker at the edge of visibility. By measuring the apparent size of the ripples in that ancient light, cosmologists could determine the shape of the universe. The result could not have been more profound. Observations showed that the universe is flat. Not almost flat, not somewhat flat. Flat within a precision so remarkable that even the margin of error inspires disbelief. The angles of a cosmic triangle add up exactly as they would on a sheet of paper. Parallel lines remain parallel. The largest sound wave in the early universe appears exactly the size that a flat universe predicts. Space, on the grandest scales we can observe, follows the rules that schoolroom geometry taught us. For a moment, this seems reassuring, familiar. Flat means ordinary, but what it implies is extraordinary. A flat universe is not the default outcome. It is not what randomness naturally produces. In the early universe, the density of matter and energy had to be balanced with incredible precision. Too much density and space would curve inward like a sphere. Too little density and space would curve outward like a saddle. The balance point is razor thin. Yet the universe sits exactly on that balance. Why? This question trembles beneath every discussion of cosmic geometry. The early universe did not have much time to adjust itself. Less than 1/1,000,000,000 of a second after the beginning, the geometry was already set. If the density of matter and energy had differed by even a tiny fraction, the universe would not look the way it does. It would not have formed galaxies. Stars would not have formed. Atoms might not have formed. The balance of geometry is written into existence itself. Einstein never knew that the universe was expanding when he completed general relativity. He imagined space filled with matter that remains still, balanced forever. When he learned that the universe expands, he abandoned the idea of a static cosmos. But the deeper geometry remained a puzzle. If the universe expands, how does the shape evolve? Expansion makes the density of matter drop. As matter becomes more spread out, its gravitational influence weakens. The shape of space depends on the balance between expansion and matter. If there had been even a slightly different number of particles in the early universe, space would curve differently. The The cosmic microwave background reveals that the universe is flat to an astonishing precision. The temperature variations in that ancient light trace patterns that act like fingerprints. From those patterns, cosmologists learned the total amount of matter and energy. They learned how much of that matter is normal. They learned how much is dark matter. They learned that most of the energy is dark energy. And from that inventory, they deduced the total density of the universe. That total density determines the shape. To be flat, the total amount of matter and energy must be just right, not more, not less, enough to counteract the natural curvature that would arise from a different total. If we describe the exact amount needed for flatness as 1, then the universe measures almost exactly 1. If it were 1.01, space would curve inward. If it was 0.99, space would curve outward. Instead, the universe sits at that precise balance. We do not know why. Cosmology does not pretend that mystery is failure. Mystery is frontier. The flatness of the universe raises deeper questions. Why should the universe begin so perfectly balanced? Why should geometry align with such extreme precision? Many researchers believe the answer lies in a period of rapid expansion near the beginning, a moment when space itself expanded faster than the speed of light. This is not a violation of physics. Nothing can travel through space faster than light, but space itself can grow faster. This rapid growth could stretch space so quickly that any initial curvature becomes flattened. The process is often called cosmic inflation. It takes a curved sheet of space and stretches it until it appears flat, much as a curved balloon can appear flat when observed from a small region of its surface. Whether inflation occurred or not, the geometry we observe is real. The shape of the universe is measured, not imagined. Flatness is not a philosophical concept. It is encoded in the structure of the ancient light. The universe tells us how it is built if we learn how to listen. Even deeper insight emerges when we consider the fate of the universe. Geometry decides destiny. A closed universe, curved like a sphere, would eventually collapse back upon itself. An open universe, curved like a saddle, would expand forever, but in a slow diminishing stretch that leaves galaxies drifting alone. A flat universe can expand forever, accelerating under the influence of dark energy. That is our universe. Its shape predicts endless expansion. If future intelligent beings could observe only their local region, they might never know the truth. They might believe the universe is static. They might believe their galaxy is the only one. They might never suspect that dark energy exists, or that dark matter sculpts structure, or that cosmic geometry once revealed everything. We live in a cosmic moment when the universe is still visible while its light still reaches us. We are witnesses to cosmic geometry before the evidence fades beyond our horizon. Space is not nothingness. It is not emptiness. Space is a fabric. It bends when touched by mass. It stretches when influenced by dark energy. It carries memory of the early universe. When you look at the night sky, you see stars scattered like grains of pollen. But beneath that scattering lies geometry. The shape of space defines the path of galaxies. The path of galaxies defines the story of time. Geometry is destiny. The flatness of the universe does not reduce the wonder. It expands it. Space could have curved wildly. Instead, it chose balance. The cosmos walks a razor line between collapse and dispersion. And that line is so exact that it strains belief. We do not live in a universe of randomness. We live in a universe of rules, laws, patterns, structure, geometry. Every moment of existence bends along that fabric. We walk through space without feeling its shape. Yet the shape determines everything. It determines whether galaxies form. It determines whether time stretches forward without end. It determines the path of light from the ancient dawn. We exist inside that shape. The universe is flat, but that flatness is not ordinary. It is the fingerprint of the beginning. For most of human history, we imagined space as emptiness. a quiet backdrop, a passive stage where stars and planets perform. Time was a separate river flowing forward, while space remained still. Einstein shattered that picture when he revealed that space and time are not separate. They form a single entity called space-time. Matter tells space-time how to curve. Space-time tells matter how to move. The fabric of reality is not rigid. It bends, it stretches, it ripples. The idea sounded impossible when first proposed. Even Einstein doubted whether these ripples could ever be measured. But the universe does not care what seems impossible. It acts according to its laws. And space-time ripples. A gravitational wave is a disturbance of space-time that travels outward from violent cosmic events. Not a wave in air, not a ripple on water, a wave in the structure of reality. When a massive object accelerates, the curvature around it changes. When two massive objects orbit one another, the curvature changes repeatedly. The disturbance travels outward at the speed of light. Imagine a pond. Drop two stones. Ripples travel outward. Now replace water with space-time and stones with black holes. The ripples are gravitational waves. To understand how radical this is, imagine stretching a blanket across a frame. Place a heavy ball on the blanket. The fabric dips. Place a smaller ball nearby. The smaller ball rolls toward the dip. That is gravity, as Einstein described it. But now imagine shaking the blanket. Ripples travel across the fabric. These are gravitational waves. They stretch space-time in one direction and compress it in another. Everything inside space-time stretches and compresses with it. But here is the difficulty. These ripples are unbelievably subtle. Even the most violent events in the universe, the collision of two black holes, create ripples that are unimaginably small by the time they reach Earth. A passing gravitational wave changes the distance between two objects by less than the width of a proton. And yet, scientists decided to measure it anyway. They built an instrument called LIGO, the Laser Interferometer Gravitational Wave Observatory. Two enormous L-shaped detectors were built, one in the state of Washington, one in the state of Louisiana. Each arm of the detector stretched for several kilometers. At the end of each arm is a mirror. A laser beam splits and travels down the two arms. If space-time stretches or compresses, the length of the arms changes and the beams return slightly out of step. The interference pattern reveals a gravitational wave. To succeed, scientists had to isolate the detector from every vibration. A passing truck could ruin the measurement. A shifting breeze could disturb the mirrors. Even the quantum motion of atoms could introduce noise. The mirrors were suspended, isolated, shielded, stabilized. The lasers were tuned with unimaginable precision. It took decades of work, thousands of people, united effort across nations. Humanity reached for a ripple in space-time. On a day in the year 2015, the detectors recorded a signal, a slight change in the interference pattern, a whisper in space-time. The signal lasted only moments, a faint chirp. Its shape matched the prediction for two black holes spiraling inward and merging into a single larger black hole. These black holes were roughly 30 times more massive than the Sun. They orbited each other faster and faster. The waves they emitted grew stronger and higher in frequency. In the final fraction of a second, they collided. The collision released more energy in that moment than all the stars in the visible universe combined. But the energy did not appear as light. It appeared as ripples in space-time. Those ripples traveled for over 1 billion years before reaching Earth. When they passed through us, they changed the distance between two mirrors by less than a fraction of the width of a proton. Yet the detectors recorded it. Earth listened to the universe. For the first time in history, humanity heard space-time. The announcement shook the scientific world. Not because the discovery was surprising, but because it confirmed something extraordinary. Einstein predicted gravitational waves in the year 1915. A century later, we caught them. We did not observe a light from the collision. We observed the motion of space-time itself. This was more than a scientific achievement. It was a new sense. Humans gained the ability to hear the universe. With gravitational waves, we are no longer restricted to light. Light can be blocked. Dust can hide stars from view. Gas clouds can obscure the core of galaxies. But nothing blocks gravitational waves. They pass through matter the way sound passes through air. They let us observe the hidden universe. Before gravitational wave astronomy, we could only watch what the universe allowed to shine. We could not see the collision of black holes. We could not detect the merging of neutron stars. We could not witness the moment when stars collapsed into singularities. These events are dark, light dies inside them, but gravitational waves carry the memory of those motions directly to us. After that first detection, more followed. Black holes merging, neutron stars spiraling together. The collision of neutron stars was particularly astonishing. Unlike black hole mergers, neutron star collisions produce light as well as gravitational waves. Telescopes around the world tracked the event. They watched as heavy elements like gold and platinum were formed in the explosion. The universe makes gold not inside stars, but in rare collisions of neutron stars. Every ring on every finger, every piece of metal shaped into art or technology, began in the collision of dead stars that sent gravitational waves across space. Gravitational waves now allow scientists to measure the universe in new ways. They can weigh black holes. They can test the speed of gravity. They can explore the properties of ultra-dense matter. These waves even carry clues about the earliest moment of the universe. If the universe experienced rapid expansion near its birth, that expansion may have left behind gravitational waves too. These waves would be older than the ancient light of the cosmic microwave background. If detected, they would allow us to see farther back in time than light will ever allow. The universe is not silent. It hums, it sings, it vibrates. Everything that moves through gravity produces waves. We are surrounded by a cosmic ocean of ripples, passing through us every moment. We do not feel them. They do not harm us. They are part of reality. They reveal the texture of space-time. Gravitational waves prove something profound. Space is not emptiness. Time is not a backdrop. Space-time is a living fabric. It flexes, it responds, it remembers motion. When a gravitational wave travels through you, every atom in your body stretches and compresses slightly. You are not separate from space-time. You are part of it. You move within its shape. This discovery changed our relationship with the universe. Light shows us what shines. Gravitational waves show us what moves. One reveals brightness, the other reveals motion. Together they reveal the universe. We began cosmology with expansion. We discovered the ancient light. We measured the first elements. We mapped the cosmic web. We revealed dark matter. We detected dark energy. And now we listen to the universe itself. Gravitational waves are the final sense we were missing. They prove that space-time is not abstract. It has texture. It is capable of motion. It can ring like a bell. And with them, we are no longer just observers of the universe. We are listeners. We have followed the evidence across the universe. We have seen that space expands. We have detected the ancient light left over from a hot beginning. We have measured the first elements forged in that early fire. We have mapped the cosmic web of galaxies. We have proven the gravity of dark matter. We have discovered the push of dark energy. We have listened to space-time ripple. We have reached the frontier. But the frontier is not an end. It is the beginning of deeper mysteries. The universe is filled with things we do not yet understand, not because we have failed, but because the universe is larger than our imagination. Every discovery widened the horizon. Every answer revealed new questions. Cosmology does not shrink mystery. It expands awareness. Consider dark matter. We know it exists. We know how it behaves. It sculpts galaxies and shapes the cosmic web. Yet we do not know what it is made of. It may be a particle that barely interacts. It may be something entirely outside the family of particles that form atoms. It might hint at a deeper symmetry in nature. We search for it in underground detectors buried deep beneath mountains to escape cosmic radiation. We search for it with particle accelerators. We search for it through the motion of galaxies. Decade after decade, we narrow the possibilities. One day, perhaps soon, its identity will be revealed. But today, it remains invisible matter known only by influence. Then there is dark energy, the force that pushes the universe apart, the energy that accelerates expansion. It dwarfs dark matter and normal matter combined. It determines the future of the universe. Yet we do not know what it is. It may be the energy of empty space itself. It may be a field that changes slowly over time. It may be a sign that our understanding of gravity is incomplete. Whatever it is, dark energy dominates the universe. And it leaves us with a question that stretches the mind. If empty space contains energy, what does that say about nothingness? Even the concept of nothing is more complex than imagination. We also do not know if the universe is infinite or finite. The observable universe is not the entire universe. It is simply the part whose light has had time to reach us. Beyond that horizon lies a region we can never observe. If expansion continues to accelerate, those regions will drift away faster than any signal can reach us. We cannot travel there. No future technology will allow it. The boundary is not a wall. It is the limit of causality. Beyond it lies darkness, not because nothing exists, but because nothing can reveal itself. There are deeper mysteries still. At the beginning of time, when the universe was unimaginably small and dense, the laws of physics as we know them could not yet operate. Matter had not yet formed. Space had not yet expanded into the shape we observe. Time itself may have behaved differently. To answer questions about that moment, we need a theory that unites general relativity, the physics of the very large, with quantum mechanics, the physics of the very small. Such a theory does not yet exist. Most paths lead into difficulty. Some theories propose that space-time is made of tiny units. Others propose that space is a hologram, where information is fundamental and geometry emerges from it. The universe may be stranger than intuition allows. Inflation, the idea that space expanded at an extraordinary rate in the earliest fraction of a second, explains many observations. It explains flat geometry. It explains uniformity. It explains the tiny fluctuations that seeded galaxies. Yet we do not know what caused inflation. We do not know what stopped it. We do not know if inflation is a property of one universe, or if it generates many. If multiple universes are produced, we would never see them. They lie outside our horizon. Cosmology forces us to face questions that may not have observable answers. Even time itself is a mystery. We treat time as flow, but physics does not assign a direction to its equations. The laws work forward and backward. Yet the universe contains a direction we cannot reverse. The expansion of space, the increase of entropy. Stars burn hydrogen into heavier elements. Galaxies collide. Black holes merge. Gravitational waves ripple outward and are never undone. Why does time move forward? Why is there a past but not a future we can visit? The universe appears to have an arrow. We can measure it. We cannot yet explain why it points only one way. And there is the question of life. The universe formed galaxies, then stars, then planets. On one planet, life arose. On one world, matter learned to observe itself. But is it the only place? The laws of chemistry and physics do not forbid life elsewhere. The universe holds trillions of galaxies, each with trillions of stars. On worlds we will never see, creatures may look up at their sky and wonder if they are alone. The universe grew complexity. Life is part of that complexity. Consciousness may be too. We are not apart from the universe. We are a product of it. As we confront these unknowns, something remarkable becomes clear. The power of cosmology is not that it answers everything. It is that it reveals which questions matter. The things we cannot explain are not failures. They are the map of what we have yet to understand. When we began this journey, cosmology was a word, a concept. Now it is a story written in the sky. Expansion, ancient light, primordial atoms, the skeletal structure of galaxies, invisible matter, accelerating space, ripples in space-time, all of it supported by observation, all of it measured, all of it real. We stand at a moment when we know more about the universe than any generation before us, yet we are surrounded by unknowns larger than our planet, larger than our galaxy, larger than imagination. That is not discouraging. It is inspiring. The universe is not finished revealing itself. Cosmology is not the study of everything. It is the study of what insists on being true. It is the discipline that listens to the universe, rather than trying to impose meaning upon it. We do not invent cosmology, we discover it. Evidence forces us to understand. Light that travels across billions of years demands that we read it. Matter that bends space-time demands that we measure it. The universe is not silent. It speaks through the motion of galaxies and the background glow of creation. In the end, cosmology is the opposite of certainty. It is curiosity sustained by evidence. It is awareness sharpened by measurement. It is the realization that we are small, yet capable of knowing the structure of space and the fate of time. When you look at the night sky, you are not seeing stars. You are seeing history. You are seeing structure shaped by invisible matter. You are seeing expansion driven by invisible energy. You are seeing light that has traveled across the curvature of space-time to reach you. The sky is not decoration. It is information. We will continue to ask questions. We will continue to follow evidence. We will continue to listen to the universe. Cosmology is not about knowing everything. Cosmology is about following the evidence wherever it leads.